Okay, let's try this example. So you have the function sine cubed x, and we want to differentiate it. Now, this is a trig function, but I don't have something more complicated than just x. But where it is more complicated, of course, is I have this power of 3. Now, when you have a power involved with your trig function, the first thing you're going to want to do is to rewrite it as sine x all to be cubed. Okay, because that's what that is essentially. Sine x times sine x times sine x is how we get sine cubed x. Okay. Now, rewriting it like this, the reason that is useful to you is because that's going to remind you that what you have here actually is something more complicated than just an x to a power. And so the chain rule boxes that we need here is this one, something more complicated than just an x to a power. So we bring down the power, take 1 away, and then of course times by the differential of whatever that is. So following this method, we're going to get 3, we're going to get sine x, we're going to take 1 away, and then we differentiate what is in here. Differentiating sine x, of course, we know is cos x. And then rewriting that, sine x to the power of 2 is of course sine squared x. So we have 3 sine squared x cos x, or it can be written as 3 cos x sine squared x. Okay, so let's try this example. Now this one is a tricky one, like we saw before our last one there with our tan square root of 2x plus 4. If you remember with that example, here, what we ended up happening is we were chain ruling, and then of course we had to chain rule again. So we had a situation where you're chain ruling twice. Now that can often happen, and it's going to happen here, okay? So the first thing that you're going to want to do the minute you see that you've got the power in the trig is of course to rewrite it like we did up here. So instead of cos cubed 2x, I'm going to do cos 2x all to be cubed. And the first chain rule I've got to deal with is the fact that I've got something more complicated than just an x to that power. Okay, so this is my first set of chain rule boxes that I want to write down. So I have this, and now I'll just follow it. So the power is obviously 3. What's in my box is cos 2x. That then is the power of 3 take away 1, which of course is 2. And now, then I want to differentiate what is in that box. Okay, so this is why I want to come over here and do a little aside, because cos 2x is again something more complicated than just an x here. So I'm going to have to chain rule this, and this is what I'm working on, of course. Cos 2x, so your chain rule boxes for this, of course, is cos, something more complicated than just an x, which is what I have here, differentiates to minus sine of that times the differential of that. Okay, so that's going to become minus sine. What goes in there, of course, is 2x. And then we'll times by the differential of that 2x. 2x differentiated is, of course, 2. And that simplifies to minus 2 sine 2x. And that's what I'm going to sub back in for here. So now I've got 3 cos 2x all to be squared, and then times minus 2 sine 2x. All right. So tidying things up, I can multiply the 3 by the minus 2 to get minus 6. Cos 2x all to be squared, we'd write as cos squared 2x. And then, of course, we have sine 2x. Okay, and again, that could be written the other way around as minus 6 sine 2x, cos squared 2x. You might have the brackets, you might not. So now we're going to look at trig inverse functions. So here's what we have in our log tables, of course, on page 25. So we have these trig inverse functions here. Now, I have to say, the way these are written aren't the easiest and most reader-friendly. They have it set up that it's not just cos inverse of x, but it's cos inverse of x over a being a number, okay? Now, it's very rare that you get an inverse function of trig where it is set up exactly in that format. So what I suggest you do to just read from the log tables is to always consider a to be equal to 1, okay? That would give the following. Cos inverse x differentiating to minus 1 over the square root of 1 minus x squared, okay? So just taking a to be 1, then that would be minus 1 over square root of 1 squared obviously is 1 minus x squared. So that's what I've got there. The reason it's easier to deal with just x is because when we come to chain rule it and we have to deal with something more complicated than just x, it becomes a lot easier to chain rule this. So instead of that, we have our boxes, of course, that's minus 1 over the square root of 1 minus, and whatever you have here goes here, all to be squared. And again, of course, we got to times by the differential, as we've done in so many cases before. So it's so much easier to understand your chain rule by dealing with cos inverse when the angle is just x on its own. Okay, so that is my advice. So doing the same thing for the sine inverse and tan inverse. Again, start off with letting a equals 1. We get the following. Okay, so this is what we get. Again, a is 1, so we have 1 over, and then square root of 1 squared, which is 1 minus x squared. So then we go to chain rule it, and it's going to be 1 over the square root of 1 minus, instead of what you have there, the x. The minute you have something more complicated than just an x, we chain rule it. So you've got the box in its place, and then times by the differential of the box. Okay, I'm just going to put a little bubble around our chain rule just to make sure we've got that clear. And again, the very useful little tip is the minute you realize you have a trig inverse function with something more complicated than just x, get your boxes down straight away. Okay, so the tan inverse, let's translate this then. Again, let your a equals 1, so that'll be 1 over 1 squared, which is 1 plus x squared. And so chain ruling that, then it'll become 1 over 1 plus whatever you have in the box times by its differential. Okay, so let's try a few examples. So take y equals sine inverse 2x plus 1, and the first thing we're going to do is get our chain rule boxes down because I have something more complicated than just an x in that box. So that differentiates to 1 over the square root of 1 minus whatever's in that box squared times the differential of whatever's in that box. So let's do that then. I've got 1 over the square root of 1 minus, and in the box is 2x plus 1 all to be squared, times the differential of 2x plus 1, that will of course just be 2. Differentiating 2x plus 1, we get 2. So tidying this up, I get 2 on the top, and then the square root of 1 minus, and then of course squaring out 2x plus 1, you're going to get 4x squared plus 4x plus 1. Okay, and that of course is 1, let's take these away then, minus 4x squared minus 4x minus 1, bring that all the way along, they cancel out, so my final answer is 2 over the square root of minus 4x squared minus 4x. Okay, so let's try this example. If you're feeling confident, press pause. So we have tan inverse, and again we have something more complicated than just an x, so it's going to be tan inverse, and that will differentiate to, of course, 1 over 1 plus whatever you have in that box squared times the differential of that. So let's follow the boxes then. 1 over 1 plus, and in there goes 1 over x all to be squared, then times the differential. Now if you need to go over here, remember how we deal with 1 over x? Your first thought is always, can you rewrite it as a power? And of course you can. So now let's differentiate it. That will be, bring down the power and take 1 away. And of course that is the same as a minus. And then x to the power of a minus. The power of a minus, remember, is 1 over. And then we have x to the power of 2, so that goes underneath. So a negative 1 over x squared is the differential of 1 over x. So let's put that back in here. Okay, let's tidy this up. So I have 1 over, then I have 1 plus. Let's square this first. So 1 squared is 1, and then I have x needs to be squared as well. So 1 over x squared times, obviously you have your minus 1 over x squared there. I want to deal with this now. So the first thing I'm going to look to do to deal with just this part of the fraction is I don't want to have this divide by x squared on the bottom. So what I'm going to do to make it an equivalent fraction, remember with equivalent fractions, all you need to do is do the same thing to the top and the bottom, and you don't change the fraction value. So because I want to get rid of this denominator of x squared, I'm going to multiply everything on the top by x squared and everything on the bottom by x squared. And then that will not change my equivalent value of this overall fraction. So multiplying the top by x squared, I get x squared times 1. Multiplying this term by x squared, I get x squared. And then multiplying this term by x squared, it will of course cancel that out. So I'll be left with 1. So let me just show you that. So I multiply the top by x squared, and then the bottom by x squared means you've got to multiply each term by x squared, and that cancels with that. So that gives me x squared over x squared plus 1. And then we're timesing by a minus 1 over x squared. Okay, and final simplifying on that, we can cancel that on the top with that on the bottom to leave minus 1 over x squared plus 1. And that is the final answer.